Have you ever stopped to think about how the incredibly complex software that runs our entire world actually gets built? I mean, from the apps on your phone to the systems that fly airplanes, it's a massive, massive undertaking. So today, let's pull back the curtain and dive in.
It really all starts with a question that, let's be honest, is pretty familiar and often painful for anyone in the tech world. Why is building software so incredibly hard? Why do we hear time and time again about these huge projects that just go over budget, miss their deadlines, or sometimes just fail completely?
Well, it really boils down to these four big challenges. Our software is getting more and more complex every single day, but the pressure to build it faster and cheaper is absolutely relentless. Just think about all the different apps on your phone that have to work together perfectly. That right there is the integration nightmare we're talking about. All of this led to what the industry started calling a software crisis.
And that's exactly where we're going to start this explainer, the software complexity crisis. For decades, the industry was basically struggling under the weight of its own ambition, using methods that just could not keep up.
Imagine you wanted to build a house, but before you could even start, you had to personally create every single brick, every nail, and every window pane from raw materials. It would be ridiculously slow and unbelievably expensive, right? Well, that's pretty much how software used to be built, as one giant custom-made thing from scratch every single time.
So, what was the big fix? It was a complete change in philosophy. The industry realized it had to stop making everything from scratch and start building with pre-made, reusable, digital bricks.
And that new philosophy has a name: component-based software engineering, or CBSE for short. The core idea is actually pretty simple, but it was revolutionary. Build large, complex systems by assembling smaller, pre-built, reusable parts.
Okay, so here is the official academic definition from one of the pioneers in the field. And yeah, I know, it's a bit of a mouthful. But the key phrases to grab onto are contractually specified interface, which just means it has very clear rules for how to connect to other stuff, and deployed independently, meaning it's a self-contained little black box. You don't need to know what's inside to use it.
But honestly, here's the absolute best way to understand it. A software component is just like a digital Lego brick. You don't care how the brick was made, right? You just need to know its shape, its color, and that those little studs on top will reliably connect to the holes on the bottom of another brick. It's simple, it's predictable, and it's incredibly powerful.
But of course, it's never quite that easy. Assembling systems from a bunch of pre-built parts, well, that introduces a whole new set of problems and trade-offs. And this brings us to the central tension of this entire approach: the promise versus the peril.
Now, in a perfect world, the process is kind of like an assembly line. First, you find the components that already exist. Then you select the best ones for what you need to do. Sometimes you have to adapt them a little, write a bit of glue code to make them fit together perfectly. And then you compose them. You snap them all together to build your final system.
So when this whole process works, it's amazing. It's a total game changer. But when it goes wrong, the results can be, well, pretty catastrophic.
Okay, let's break this down a bit. The promise is huge. You get stuff done way faster, the quality is higher because you're using parts that have already been tested, and everything is more consistent. But the peril, the risk, is just as real. It costs a lot more upfront to build a good, reusable part. Then, maintaining that part for lots of different applications gets super complex, and you're always running the risk that parts from different creators just won't play nicely together.
And to put a number on that peril side of things, check this out. It can take up to 5 times the effort to create one high-quality, truly reusable component compared to just building a quick single-use one. That's a massive upfront investment.
So really, that's the crucial point. Component-based software engineering is a bet. It's a high-stakes gamble that spending a lot more time, money, and energy right now is going to pay off exponentially down the road through speed, quality, and reuse.
So, how did that gamble pay off? Well, decades after this idea really took hold, we are still grappling with its implications. And that brings us to our final section, the future of assembly.
Even today, there are some enormous unanswered questions. How can you really, truly trust a component you didn't build yourself? Should there be some kind of universal certification for quality? How can we possibly predict what's going to happen when we connect all these different parts together? And maybe the biggest question of all, who's responsible for maintaining these parts years after they've been created?
And all of these technical challenges, they all point to a much deeper, much more human question. It's a question that goes way beyond engineering and into the territory of trust, accountability, and even liability.
So I'll leave you with this final thought. When a complex system built from hundreds of different parts made by hundreds of different people fails, who is to blame? Is it the architect who assembled it all, or is it the original maker of that one faulty part? It's a question the tech industry is still wrestling with, and the answer is going to shape the entire future of software.